Alright, today we're going to explain the Cheerio effect. What is the Cheerio effect, you ask? Well, watch and learn. Notice how the Cheerios are clumped together or stuck to the wall. If you break them apart, you'll notice that after a short period of time, none of the Cheerios are separate anymore. They'll all clump together or either move to the wall. This is known as the Cheerio effect. This example can be misleading, however, because it may lead you to assume that all floating objects will clump together or go to the wall. This is untrue, however. Through a series of 7 experiments, we will show that the Cheerio effect depends on the density of the object compared to the density of the liquid, as well as surface tension. The first experiment will explain the interaction between a Cheerio and the wall of the bowl or glass, whatever you have. In this experiment, we'll be using a bottle top, but in theory, it should be about the same as a Cheerio. Nearly everyone knows that if you have a liquid, such as water or milk, it will form this kind of meniscus curve with the wall of your container. So the liquid will climb up the side of the wall, so it'll be at a higher level as you get closer to the wall. You'll see in the drawing that there are 3 main forces acting on the bottle top. There's gravity pushing downwards, you have buoyancy pushing upwards, keeping it afloat, and surface tension also pushing upwards. In this experiment, it's important to note that the bottle top is less dense than the water that we're floating it in, so the buoyancy force will be greater than the gravitational force. The net result will be that the bottle top will attempt to rise to the highest point that it can, without, of course, leaving the surface of the liquid, because then there would be no buoyancy force. It does this by moving up the meniscus curve, causing it to appear to be attracted to the wall. We'll demonstrate this now. A bottle top in water. If I drop it in, you can see that even if I keep it around some distance near the wall, it'll slowly attract towards the wall and eventually stick to it. If I pull it away, it'll just go back. The second experiment will explain the attraction between 2 Cheerios, or in this case bottle tops. The effect is actually very similar to what we saw in the first experiment. You'll notice here that these rectangles are the bottle tops, and you'll see that meniscus curve is actually forming on either side of the bottle top. This wasn't shown in the first experiment because the meniscus curve caused by the wall was so much greater than that from the bottle top. However, it is enough to cause the 2 to attract. As they approach each other, because the bottle tops are less dense than water, the buoyancy force will win over the gravitational force, causing the bottle tops to follow each other's meniscus curves, seeming to cause the 2 to attract. We'll show this over here. You'll see the bottle tops separated some distance. And if you take them apart, they will just go back together. The green one will even follow the blue one around. And that is due to the buoyancy force causing them to follow each other's meniscus curves. Experiment 3 shows the interaction between a pin and a wall. Now this is a little different from how Cheerios would behave, because the pin is actually more dense than the water that it's floating in, meaning that the gravitational force is actually greater than the buoyancy force. In this case, the only reason that the pin stays floating is due to surface tension. If we submerge the pin, it would sink to the bottom. Being that the gravitational force pushing down is greater than the buoyancy force pushing up, if we bring this close to the wall, the greater gravitational force will push the pin down this curve, as opposed to the bottle top, which followed the meniscus curve up it because the buoyancy was greater in that case. So let's test this theory out over here. We'll see that as we bring the pin close to the wall, it will repel. We can try it again. It doesn't even have to be all the way at the wall, and you can see that it repels because it is denser than water and following the meniscus curve back down. We saw in experiment 3 that for the first time the pin and the wall actually repelled each other, as opposed to in the first experiment the bottle top and the wall attracted and the two bottle tops attracted. So let's see what would happen if we have two pins. Obviously, again, both pins are denser than water, so the gravitational force is greater than the buoyancy force. The only reason that it stays floating is because the buoyancy force plus surface tension is greater than the gravitational force. Because of this, the water actually curves down around the pin, because the surface tension is the only thing keeping it floating. It does this on both pins. So as they approach each other, because gravity is greater than the buoyancy force, we would expect that the pins would follow the curve created by the other pin, and we would guess that they would attract each other. So let's do an experiment and see what happens. Bring this pin a little closer, and I don't know if you saw it. I'm moving. Fifth experiment, we're going to look at the interaction between a pin and a bottle top. Over here we have the bottle top. As before, you can see the meniscus curves up around it because the buoyancy force is greater than the gravitational force. Over here, the pin, the surface of the water curves down because surface tension has to assist the buoyancy force in order to keep it afloat, because the gravitational force is greater than the buoyancy force. If we bring them together, we would expect that as we brought the pin near the bottle top, it would have to rise along this curve in order to be attracted and stick to the bottle top. Because gravity is greater than the buoyancy force, it will tend to go down the curve and stay away from the bottle top. If we look at the bottle top and bring it closer to the pin, we'll see that it will have to go down this curve in order to be attracted to the pin. Because the buoyancy force is greater than the gravitational force, the buoyancy force will win and it will push it up this curve, causing it to repel. So either way you look at it, the pin and the bottle top should repel each other. So let's look at this example. As we bring the bottle top close to the pin moves away because they repel each other. If we move the pin closer to the bottle top will also repel. So our prediction was correct. Experiment 6 is very similar to experiment 5 in that we have a bottle top and a pin both floating in water. The important difference in this experiment is that we've filled in the bottle top so that it's now actually more dense than the water it's floating in, just like the pin. The result is that for both the bottle top and the pin, the gravitational force is greater than the buoyancy force. However, due to surface tension, they both stay afloat. So the question once again is, will they attract or repel each other? You can see that for both the bottle top and the pin, the water curves down. So if we brought one of them towards the other, because the gravitational force is larger than the buoyancy force, for example, if we brought the bottle top towards the pin, it would follow this curve down and appear to be attracted to the pin. The same thing would happen if we brought the pin towards the bottle top. So let's do an experiment and see what happens. So we'll bring the bottle top. In experiment 5, when we brought them close, they repelled, but here you can see that they attract. And the pin actually follows the bottle top if we try to move it. So, okay. This is the final experiment, experiment 7. We have a filled bottle top, and we're going to see how it interacts with the wall. It's similar to experiment 1, except that now the bottle top is filled, so the gravitational force is greater than the buoyancy force, and it's floating only because of surface tension. As before, the water curves down around the bottle top, and it curves up towards the wall. So if we brought the bottle top towards the wall, we could bring it to some location near the wall, and gravity, which is greater than the buoyancy force, would cause it to go back down the curve. So we'd expect that the wall and the bottle top will repel each other. Let's see what happens. So even if I put the bottle top next to the wall, it repels. In the previous 7 experiments, we've seen that whether or not two objects will attract or repel each other is determined by the density of the object compared to the density of the liquid, because this determines whether or not the gravitational force or the buoyancy force will be larger. It also depends on the surface tension, because that will keep the object floating even if the gravitational force is larger than the buoyancy force. We can use what we learned in these 7 experiments to think about a theoretical 8th experiment that is similar to the first experiment that we did. However, instead of using water, which would curve up at the wall, we can use a non-wetting liquid, such as mercury, which would curve down, and think about what would happen. Obviously, we can't do this experiment because it uses mercury, and that is very dangerous. But anyway, here we see that the buoyancy force is greater than the gravitational force. So if we were to bring this bottle top towards the wall, the buoyancy force would win over the gravitational force, pushing it up towards the curve, away from the wall. So unlike in the first experiment, where the bottle top was attracted to the wall, it would now repel, because the liquid we're using has different properties. So that concludes our bonus project. Thank you.